We know that a vector has both a magnitude and a direction. I want to talk about how we find the magnitude or the length of a vector. And let's start with this vector v. We'll let it be the vector 4, 5. So I could draw a picture of that vector. Here it is. Here's the vector v. And I want to know its length. Well, we know we could draw a right triangle because we know the components. We know in the x direction it goes 4 units, and in the y direction it's going 5 units. So we have our right triangle, and we know how to find the length of the hypotenuse in a right triangle. So let's find the magnitude, and I haven't even mentioned the notation for magnitude. And it varies from book to book. Sometimes you see it looking like this, and sometimes it looks like this, looking more like the absolute value. Sometimes with a double bar, sometimes with those single bars looking like an absolute value, and you do see both. But now let's get back to finding that magnitude. You know that the length of the hypotenuse of this right triangle would be the square root of 4 squared plus 5 squared. And we can simplify that, and we have the square root of 16 plus 25, which we know is the square root of 41. So let's write this in general. If we have a vector v, and we'll let the x components and y component be v1 and v2, then the magnitude or length of v is given by the square root of v sub 1 squared plus v sub 2 squared, just as we did in the previous problem, because it comes from the Pythagorean theorem. So let's do this next problem, and we won't need to draw a picture to do it. So the magnitude of v, when the vector is -1, 5 in component form, is the square root of -1 squared plus 5 squared. And we can simplify that. We have 1 plus 25, or the square root of 26. And we know the magnitude of this particular vector. Let's do one more. This one, I just decided to toss some fractions in there. Doesn't change what we do. We have the vector that has an x component of 3/5 and a y component of 4/5. So the magnitude of v, oops, I didn't put the vector symbol over the v here. I should have. And here as well. Remember, if you're writing it by hand, you need an arrow over that v to denote the vector. In your textbook, you'll see it just as bold, but when we write it by hand, you need that vector symbol above it. So we have the square root of 3/5 squared plus 4/5 squared. Well, we can simplify that. We have 9/25 plus 16/25. And let's see, that is 25/25, which is 1. And we know the square root of 1 equals 1. So the magnitude of this vector is 1, or its length is 1. We say that a vector whose length is 1 is called a unit vector. And sometimes in applications, it's useful to find unit vectors. So if you're given a particular vector, we're going to do this problem here. I want to find a unit vector. That means a vector of length 1 that is in the same direction as this vector. Now, if this vector is, we don't know the length of the vector yet, but if we can multiply it by a number and make it longer if we need to, or multiply it by a number smaller than 1, like 2/3 or 5/7, multiplying it by 2/3 or 5/7 will make it shorter. Multiplying it by 5 or 10 will make it longer, right? But we'll multiply it by the appropriate number to make it either longer or shorter to make it unit length. So let's jump in, and we need to know how long it is first. So let's find its magnitude. The goal, remember, is to find a vector that is in exactly the same direction, but is 1 unit long. So here we go. Let's find the magnitude. The magnitude of v is equal to the square root of 5 squared plus 12 squared. And we have the square root of 25 plus 144 is 169. But 169 is a perfect square. It is 13 squared, so its square root is just 13. So this vector is of length 13. We want it to be of length 1. So our unit vector we'll find by taking the vector 5, 12 and multiplying it by, let's see, what do we need? We need it to be 1/13 as long. We're going to multiply it by 1/13 and we'll have the unit vector. If we multiply by 1/13, we'll have 5/13 and 12/13 as the component form of the vector that is unit length. So it's just like this. And it would be this vector, 1/13 as long as this particular vector. Notice another way of looking at this right here is it's the vector v divided by the magnitude. We have this 5, 12 as the vector v, and we're dividing it by the magnitude to make it be length 1. Let's see that written out a little more formally right here. The unit vector that is in the same direction as vector v can be obtained by dividing v by its magnitude. So let's do that. We'll just use the formula. So we're going to find a unit vector in the same direction as vector v. So here we go. The unit vector will equal 7, -2 divided by the magnitude. So we take the square root of 7 squared plus -2 squared. Let's simplify. So we have the vector 7, -2 that is being divided by, what's that value? The square root of 49 plus 4, that's the square root of 53. And if we write that by taking care of this square root of 53, we'll have 7 over the square root of 53, comma, -2 over the square root of 53. So this vector is in the same direction as this. It just happens to be 1 unit long. There are some useful unit vectors that are actually very common. And they are the unit vectors that are in the x direction and the y direction. We let I be the unit vector in the x direction, and j is the unit vector in the y direction. And if we have a vector v that is, let's say, v sub 1, v sub 2, those are its components, we can write it as v sub 1 times 1, 0 plus v sub 2 times 0, 2. If we added these two together, we would have that vector. But notice that is v sub 1 times I plus v sub 2 times j. And we have an alternate way to write a vector. And both of these are common notation. So if we have a vector v that is, say, 211, we could equivalently write it as the vector that is 2i plus 11j. What I want to do now is just practice some of the problems that we do using vectors, using this notation now. The way in which we do the problems won't change at all. We're just getting used to this notation. I thought we'd practice a few different types of problems. So here we are. We're going to let the vectors be these two. The vector v will be 6i minus 7j, and the vector w will be negative 2i plus j, and we're going to find a few things. Let's start with 3 times the vector v. We already know when you multiply a vector by a scalar, that scalar gets multiplied by each component. So this would be 3 times 6i minus 6j. So if we multiply 3 by each of those, we'll get 18i minus 21j. And notice I'm putting that vector symbol above the I and the j. Let's move on. Let's do the next one. We're going to find the magnitude of v. Again, it is not a different problem just because I'm using this ij notation instead of the chevron notation. We're going to find the magnitude of v by taking the square root of 6 squared plus negative 7 squared. So we have the square root of 36 plus 49. And that's equal to the square root of 85. Now 80 square root of 85, we can't simplify, so that's done as well. Let's do the next one. The sum of two vectors. Remember, we add the horizontal components together and the vertical components together. So v plus w is 6i minus 7j. Whoop, I didn't leave enough space for this. Plus negative 2i plus j. And that equals, we'll add the x components together. We have 6 plus negative 2, that's 4. So we have 4i, and we have negative 7j plus 1j, that's negative 6j. So we have added v plus w. Let's do this last one. We have 7 times v minus 2 times w, probably just as you would expect. 7 times 6i minus 7j minus 2 times negative 2i plus j. We'll multiply the first vector by 7 and we get 42i minus 49j. And for this one, you can either distribute the positive 2 and leave the minus out front, or we can distribute the negative 2 and change it to a plus. Either way is fine. I'll just make this a plus, and we have now positive 4i, because we had negative 2 times negative 2, minus 2j. And when we combine these components, we have 42i plus 4i, that's 46i, and a negative 49j and a negative 2j is minus 51j. And now we have 7 times vector v minus 2 times vector w. Let's do one last problem, bringing us back to a unit vector now with our new notation for our vectors, our I and J notation. So we're to find a unit vector in the same direction as W. So remember, our unit vector will be the vector W divided by its magnitude. And when we're done, we'll have a vector that is 1 unit long. So let's write negative 2I plus j in the numerator. And in the denominator, we need the magnitude of that vector, so it's the square root of negative 2 squared plus, coefficient of j is 1, 1 squared. So we have negative 2I plus j divided by, let's see, what do we have? 4 plus 1, that's 5, so we have the square root of 5. So our unit vector is negative 2 over the square root of 5I plus 1 over the square root of 5j. And now I hope you'll go practice working with unit vectors and magnitudes.